In this class, we learned to use SOLIDWORKS software, the engineering design process, teamwork, and develop our communication skills. The goal was for us to work in a team on an engineering design idea and take it from a concept to a prototype. Did you know that the average cost for a hand prosthetic, which doesn't move but molds, is $5,000? While an active hand prosthetic's average cost, which means it's an electronic prosthetic and can function, is $50,000? Well, our project is a low-cost 3D printable prosthetic solution for hand amputees starting at the wrist. In our design, we have designated the material as EPLA+, a sustainable corn grain-derived high-impact plastic. This will provide an accessible and affordable option for those who cannot currently receive a prosthetic that still allows for a reliable and convenient use. We chose this project because we wanted to provide a solution to hand amputee individuals that lack the financial ability to receive a functional prosthetic, but in a sustainable way. For this class project, we needed at least 3 sub-assemblies that would make up one final assembly. Our sub-assemblies are the fingers, thumb, palm, and wrist attachment. Each of us brainstormed how we would design our sub-assemblies and how they would interact.
Throughout the design process, we learned multiple different steps to creating a product, including initial orthographic sketches, modeling with SOLIDWORKS, creating SOLIDWORKS detailed drawings, and running simulations. We learned to test our product's strength, its resistance to temperature change, how to test for interferences, and as well as clearances. Furthermore, we learned about the various variables that accumulate to produce our product's environmental impact. Some of these include site of manufacturing, method of manufacturing, material choice, transportation of raw and finished goods, energy usage, and the end-of-life processes of our product. To encourage sustainable choices, we've dedicated our material of choice as eSun's EPLA+. This is a bio-derived, high-strength plastic polymer which comes in a variety of colors.
This is my thumb assembly made up of the dynamic end, middle, and tip.
Here you can see the components of the finger assemblies. Each is comprised of a tip, mid, and end joint. Each are secured with 1.5mm pins which allow for rotation. Spring-loaded rubber bands encourage the system to return to normal position when the internal tension wire releases pressure. We explored a variety of fasteners and tensioners for our system. Many tests were done to find the best choices of materials. We even attempted to 3D print our own pins. After much testing though, we decided to use 304 stainless steel pins, a number 2 countersunk flathead screws, steel braided cables, orthodontic rubber bands, and any basic spring.
A challenge was making the holes for the wire in the palm and dynamic thumb end parts. By going beyond the basics of the course with planes, we achieved our design. As you can see, there are many planes and hidden hole shafts.
In the future, we would like to include affordable and accessible electronics, improve durability, and find more natural ways to engage the system. Furthermore, we want to start outreach to various facilities such as hospitals, VAs, and homeless shelters.
Constant communication when facing design challenges and making updates made reaching a prototype easier.
We'd like to thank you for stopping by, and if you have any questions or suggestions, please feel free to let us know.